Yes, good morning, students. Yesterday we have started mechanical properties of fluids. That part we will complete. And again, that part we will complete today. Mechanical properties of fluids. Yesterday we have seen that up to Pascal's law. Next, relative density. Relative density or specific gravity both will be same. RD for relative density. Relative density, it is defined as density of the body divided by density of water. Density of the body divided by density of water is called as the relative density. This, whenever we are whenever we are heating the water, let us suppose water is there in a vessel. Water is there in a vessel. If we are heating the water, 0 degrees centigrade to 4 degrees centigrade, 0 degrees centigrade to 4 degrees centigrade, temperature of the water while you are increasing, density, instead of increasing the volume, that decreases. Volume of the water that decreases. The volume will be maximum, means what? Minimum volume will be there. That means density will be maximum at 4 degrees centigrade. Density will be maximum at 4 degrees centigrade. After 4 degrees centigrade, it starts expanding. It will start expanding. So up to 4 degrees centigrade, instead of increasing its volume, it decreases. Instead of increasing, it decreases. So loss of the flotation, whenever we take, loss of flotation. Let us suppose density of the rho, I am taking rho for density. Density of the body is less than that of the density of the liquid. Density of the body is less than that of the density of the liquid. In such case, body will float. Let us suppose density of the body is less than that of density of the body is less than that of density of the liquid, then it will float. If density of the body is equals to density of the liquid, density of the body is equal to density of the liquid. In such case, body may be anywhere between the surface to bottom, anywhere it may have. It will be there. Let us suppose body density is equals to density of the liquid, then body may be anywhere between the surface of the liquid to bottom of the liquid. Third case, if density of the body is greater than the density of the liquid, then it will sink. Density of the liquid is greater than that of the density of the density of the body is greater than that of the density of the liquid, then it will sink. So then whenever we take that weight of the body that is taken as V rho and G. V rho G. V for volume, rho for density, G is the acceleration due to gravity. What is the weight? It is a product of mass into acceleration due to gravity. So then density is equal to mass by volume. Therefore, mass is equal to volume into density. Then W is equal to, in the place of mass, we may write volume into density. V rho G. Weight will be equal to V rho G. V for volume, rho for density, G is acceleration due to gravity. Like this, we may take. So then equation of continuity. Equation of continuity states that the product of the product of area of cross section and velocity is a constant. That means, let us suppose two different area of cross sections are there. Area of cross section, it is taken as A1, it is taken as A2. A1, A2 are the area of cross sections. Let us suppose V1 is the velocity at this and V2 is the velocity at this area of cross section. According to equation of continuity, AV is a constant. AV is constant. Otherwise, A is inversely proportional to V or V is inversely proportional to A. Like that also we may write. Or we'll write that A1 V1 is equal to A2 V2 we may write. Or from this, V is inversely proportional to area of cross section. What is A? A for area of cross section. Then V is inversely proportional to pi r square. Then we'll write that V is inversely proportional to r square. Then V is inversely proportional to r square. From that, V1 by V2 is equal to R2 divided by R1 whole square. V1 by V2 is equal to R2 by R1 whole square. Like this, we will take. This is from the equation of continuity. When the liquid is flowing, liquid flow may be it is some disturbances there. Then liquid flow may be streamline flow. Streamline flow means that liquid flow is liquid speed is less. It is a streamline flow. Steady flow of the liquid will say that. If the liquid velocity that increases, that is unsteady flow, means it may be uneven flow. We'll say that little variation it will be there. If the speed of the liquid that increases a critical value, then it is called as the turbulent flow. If the speed of the liquid that increases greater than the critical value, then it is called as the turbulent flow. This is called as the it's called uneven flow, means unsteady flow. We'll say that. This is called as the streamline flow. So fluid may be, it's called streamline flow, or maybe compressible. Compressible means what? Liquid we can reduce its density. If you are able to reduce its density, that will say compressible. Liquid may be streamline flow or turbulent flow, or liquid may be compressible or incompressible. Compressible means we can change the density. Incompressible means we cannot change the density. Like that, liquid flow may be steady flow or streamline flow or turbulent flow, or it may be viscous and non-viscous. Viscous means what? Viscous force. Viscous means what? Density. Viscous force will be there whenever the liquid that is flowing. Let us suppose one canal. We consider one canal or one a pipe. So in a pipe, water is flowing like this. This is the top layer. Top layer. This layer that opposes the next layer speed. This is second layer speed will be reduced by the first layer, and the second layer that opposes the speed of the next layer. Like that, layer to layer speed of the liquid that decreases because the top layer that opposes the speed of the next layer. So like that, layer to layer liquid that reduces its speed. Then the force acting among the different layers of the liquid is called as the viscous force. So the viscous force acting that depends upon area of cross section of the pipe, and it depends upon velocity gradient. So velocity at the top it's more, and velocity of the layer which is at the bottom is less. So F is proportional to A into dV by dx. Or to replace the proportionality, we multiply with a constant. F is equal to eta into A dV divided by dx. This coefficient of the viscosity eta is equal to F divided by A into dV by dx. Otherwise, coefficient of viscosity eta is equal to pressure divided by velocity gradient. Pressure divided by velocity gradient. Velocity gradient is nothing but distance, velocity difference divided by distance. The unit of this coefficient of viscosity is poise. Poise is the unit of the coefficient of viscosity. Otherwise, we'll write this is a Pascal. F coefficient of viscosity Pascal meter per second. Pascal second it is. We may write Pascal second or poise. CGS unit is poise. CGS unit is poise. SI unit is Pascal second. PA for Pascal. S for second. Pascal second. Right. According to that Torricelli's law. According to the Torricelli's law, the liquid that is coming from a pipe that follows the equation of a freely falling body. Let us suppose from the tap is at certain height. So water is coming from the tap. This will satisfy the equations of motion. What is that equations of motion? Whenever we take that equations of motion, the liquid that is coming from the pipe that will follow the equations of motion. On reaching the ground, velocity will be equal to square root of 2gh. This is what Torricelli's law. Torricelli's law states that the liquid that is coming from a tank, open tank, liquid that is coming from the open tank will follow the equation of continuity, equations of motion. It will follow the equations of motion. That means the velocity of the body that is touching the ground, v is equal to square root of 2gh. So time taken t is equal to square root of 2h divided by g. Range of the water covered will be range d is equal to horizontal velocity into time of flight. Then d is equal to v into square root of 2h divided by g. Like this, we may write. This is according to Torricelli's law. And Bernoullis equation. When we take that Bernoullis equation, or Bernoullis theorem also will say that. It states that a different area of cross sections of the pipes we have taken, which are these are at different heights from the ground. These are at different heights from the ground. This is at a height h1 and height h2 from that. This is the area of cross section A1. Its area of cross section is taken as A2. Its area of cross section is A1, and its area of cross section is taken as A2. Then velocity at this point is taken as V1. Velocity at this one is taken as V2. V1, V2 are the velocities. Then according to Bernoullis equation, pressure at this point A1 is taken as P1 plus half rho V1 square plus rho GH1 is equal to pressure P2 plus half rho V2 square plus rho GH2. This is the equation, Bernoullis theorem. This is called as the Bernoullis theorem. Right? So then whenever we take Stokes formula, it states that then viscous force acting on the drop sphere will take that F is equal to 6 pi eta RVT. Viscous force acting on a sphere of radius capital R or raindrop of radius small r. Viscous force acting on the raindrop of radius small r or the sphere of radius small r, it is taken as F is equal to 6 pi eta RVT. Then terminal velocity, VT for terminal velocity. Let us suppose raindrops they are falling. The terminal velocity VT is equal to 2 by 9 R square G divided by eta into rho minus sigma, where rho is called as a density of the fluid. Density of the body, sorry. Rho is called as the density of the body and sigma is called as the density of the fluid. Rho is density of the body, sigma is the density of the fluid, right? According to this, terminal velocity VT is proportional to R square. Terminal velocity VT is proportional to R square. VT1 divided by VT2. VT1 divided by VT2 is equal to R1 by R2. R1 by R2 whole square. VT1 by VT2 is equal to R1 by R2 whole square. That we will take. Next, Poiseuille's formula. Poiseuille's P-O-I-S-E-U. Poiseuille LLI. Poiseuille's formula. The spelling will be like this. Poiseuille's formula. According to the Poiseuille's formula, the volume of the liquid collected, let us suppose it is a pipe. Pipe of length L is taken. Pipe of length L is taken. The volume of the liquid collected. The volume of the liquid collected in a pipe. Volume of the liquid that is collected in a pipe. This is the volume of the liquid that will be collected in the pipe. Volume of the liquid collected in a pipe is equal to pi p r power 4 divided by 8 eta L. Pi p r power 4 divided by 8 eta L. This is the Poiseuille's formula. This is called as Poiseuille's formula. Then we may write this one. V is equal to P divided by 8 eta L divided by pi r power 4. This is called as the resistance, where R is for liquid resistance. R is equal to 8 eta L divided by pi into r power 4. This is called as the liquid resistance. Therefore, volume of the liquid collected in the in a vessel, V is equal to P divided by R. P for pressure, R is for the resistance offered by it. Then whenever we take the work done, first of all, we go for surface tension. Every surface of the liquid, it will maintain certain stiffness. Every surface of the liquid will maintain certain stiffness that we call surface tension. Every surface of the liquid will maintain certain stiffness is called as the surface tension. Every surface of a liquid that will maintain certain stiffness that we call surface tension. Surface tension defined as a force acting per unit length. Surface tension we may represent with S or with the T also. Surface tension we may represent with S or with T. T for surface tension. Surface tension is nothing but force acting per unit length. Force acting per unit length of an imaginary line. It is taken as, let us suppose this is that liquid surface. On the, it's a vessel. In the vessel, liquid surface is there. This is a liquid surface. On the liquid surface, if you draw an imaginary line, this is the imaginary line. The imaginary line drawn, force acting on the imaginary line drawn per unit length is called as the surface tension. This is the imaginary line. On this imaginary line, either sides that force will act. So the force acting per imaginary line of the liquid surface is called as the surface tension. The unit of the surface tension will be Newton. Unit of the surface tension will be Newton per meter. It will be Newton per meter. Our CGS unit is dyne per centimeter. It's a dyne per centimeter. So 1 Newton per meter is equal to 1 Newton per meter is equal to 10 power 3 dyne per centimeter. 10 power 3 dyne per centimeter. So then dimensional formula, if you write for this surface tension, M1 L0 T power minus 2. This is the dimensional formula. When we want to lift different bodies from the surface of a liquid, then the force required lift an object from the liquid surface. The force required to lift an object from the liquid surface. It is that a wire of the length L is there. If you want to lift that wire, let us suppose this is that imaginary line, will take it. This is that on this imaginary line will take it. This is the wire of length L is there. So both sides that we have to consider, free surface will be there. Free surface will be there on both sides. That's why L and L, 2 L's we have to take, 2 lengths we have to take. Force required to separate a rod, uniform wire or uniform rod. Instead of this, I write that uniform rod of length L. If you want to remove that or lift that uniform rod of length L from the surface of the liquid, F is equal to surface tension into two sides of free surface will be there. That's why F is equal to T into 2L. F is equal to T into 2L. This is that force. Next, circular disc. If you want to remove that circular disc, force required, F is equal to surface tension into only one surface area is free. for this circular disk, if you take that outer surface only free, only one surface will be free. That's why surface tension into 2 pi r, that circumference of the circumference of this disk is taken as 2 pi r. R is the radius. Then circular ring. For the circular ring, the force required to remove the circular ring from the surface of the liquid is F is equal to 2. One surface is 2 pi r, and inside also one free surface is there. 2 pi r plus 2 pi r. This 2 into 2 pi r, that which T is T into 4 pi r. So force required to lift a circular ring from the liquid surface, whose surface tension is taken as T is. If you want to lift that circular ring from the surface of the liquid, force F is equal to T into 4 pi r. Then square plate, if you want to remove from the surface of the liquid, the force required is to remove that square plate from the, square plate from the, this is that square plate. This is square plate we have to lift from the liquid surface. Then length L and L. So this is square plate. Force required to separate that square plate is it will be 4 sides. Length side length is taken as A. 4 sides will be there. F is equal to T into 4A. T into 4A. Or whenever we take that square loop, to remove that square loop. Here outside four sides are available. Inside also 4 sides. Inside also 4 will be there. Then F is equal to T into 8A. This is the force required to lift this square loop from the surface of the liquid is F is equal to T into 8A. So like this for rectangular one, or for the spherical one, for annular ring, elliptical plate, for all of them will take. So for rectangular plate, if you take rectangular plate, for the rectangular plate, it is that rectangular plate of length L and breadth B. So breadth B and length L. So force required F is equal to T into rectangular plate. It is a rectangular plate. So F is equal to force T into 2 lengths and 2 breadths are there. 2 into L plus B we will write. This is the force required to separate different objects from the surface of the liquid. We have to lift whenever we want to lift that. Then work done in making that liquid bubble, or work done in making in blowing the soap bubble, that are important. Work done in making, in forming a liquid drop of radius capital R. Work done in lifting a drop, work done in forming a liquid drop of radius capital R is. So then work done W is equal to surface tension into surface area. Surface area will be equal to 4 pi into R square. Surface tension into surface area. Surface tension into surface area. 4 pi R square. T into 4 pi R square. Then work done in forming that liquid drop of the radius capital R. in forming a liquid drop of radius capital R, we need the liquid drop of radius capital R. When we want to form, the work done is taken as T into 4 pi R square. Then liquid drop of radius capital R is there. Liquid drop of radius capital R is there. This we have to increase from radius R1 to R2. Initial radius is taken as R1 and it should be removed from, means it will be increased its volume from R1 to R2. So initial radius is taken as R1 and the radius of the liquid bubble should be increased from R1 to R2. Therefore, the work done is therefore equal to T into 4 pi into T into 4 pi into R2 square minus R1 square. W is equal to T into 4 pi into R2 square minus R1 square. This is the work done in forming a soap bubble, a liquid drop, and increasing that radius of the liquid drop from R1 to R2. Whereas if it is for the work done in blowing, if it is the work done in blowing soap bubble, work done in blowing a soap bubble of radius capital R. This is for the liquid drop, only one surface will be available, and for the soap bubble, two different surfaces will be there. Two inside surface will be free, as well as outside surface also be. So two free surfaces will be there. Two free surfaces will be there for the liquid drop. For the soap bubble. For the soap bubble, two free surfaces will be there. This surface is free and this surface is also free. Therefore, work done in blowing a soap bubble of radius R, W is equal to T into 8 pi R. T into 8 pi R. This is the work done in blowing a soap bubble of radius capital R. If you want to increase the radius from R1 to R2, so a soap bubble is there. Soap bubble of radius R1 is there. This radius R1 to R2 we have to increase. The radius of the soap bubble initially R1 is taken. Its radius should be increased to R1 to R2. Initial radius is taken as R1. This should be removed from, means increased R1 to R2. Then the work done, W is equal to T into 8 pi into, here 8 R square also will be there. So W is equal to T into 8 pi R square. This W is equal to T into 8 pi into R2 square minus R1 square. Work done in increasing that radius of the soap bubble from R1 to R2 is taken like this. So then whenever we take that work means radius of the big drop and radius of the small drops, if you take that, let us suppose this is important. A radius of a liquid drop of radius capital R is split into n identical drops. A liquid drop of radius capital R is split into n identical drops. A liquid drop of radius capital R is split into n identical drops. Then a liquid drop of radius capital R is split into n identical drops. Then we take that a drop of radius capital R is there. It is a drop of radius capital R. It is split into n identical drops of each radius small r. It is split into n identical drops of each radius So radius of a drop is taken as a capital R. This we have to split into n identical drops, each of radius small r. Then we'll say that volume of the big drop is equal to volume of all n small drops. Volume of the big drop will be equal to volume of all n small drops. Therefore, we'll write that volume of the big drop is equal to volume of the small drop. Volume of the drop will be equal to 4 pi third pi r cube. Then n into 4 by third pi r cube. N into 4 by third pi r cube. Then 4 by third pi, for that 4 by third pi get cancelled. There r cube is equal to n into small r cube. R cube is equal to n into small r cube. Therefore, r is equal to n power 1 by 3 into r. So this is the relation between the radius of the big drop and radius of the small drop. Then work done in forming the energy needed to combine, or energy needed to split the drop, or energy needed to combine the small drops as a big drop. So then energy or the work done needed to split this big drop of radius capital R into n identical drops, a radius of the capital R into n identical drops. Then work done is equal to work done in splitting it, surface tension T into 4 pi r square, 4 pi into r square, T into 4 pi r square into n power 1 by 3 minus 1. Otherwise, this is taken in terms of capital R. In terms of small r also we may write that. Same formula. Work done in splitting the drop, W is equal to T into 4 pi small r square, 4 pi into small r square into n minus n power 2 by 3. T into 4 pi r square into n minus n power 2 by 3. This is the work done in blowing that, in splitting the drop into capital drop into small identical drops. Okay, we will go to that numerical part. These are the major synopsis. Then see, an iceberg floats. An iceberg. This is 2021 CET. All these are the previous year's CET problems. 2000, check the 2020 it is given. This problem is given 2020 case-set. Iceberg floats in water with part of it submerged. What is the fraction of the volume of iceberg submerged in the submerged if the density of the ice is 0.917 gram per centimeter cube? It is given density of the ice is given. Density of the ice is 0.917 gram per centimeter cube. Gram per centimeter cube. Then density of the water is 1000 kg per meter cube. If it is SI unit, 1000 kg per meter cube. If it is a CGS unit, 1 gram per centimeter cube. So density of the water in CGS system is 1 gram per centimeter cube. Then an iceberg that floats, an iceberg floats in water with part of it submerged. Certain portion is submerged in the water. That iceberg, certain part of the iceberg that submerged in the water. It is given that it is submerged in the water. Certain part is submerged up to some extent that is submerged in the water. So then weight of the iceberg will be equal to weight of the water that is displaced. Weight of the water that is displaced means it will remove the water and it occupies that volume of the water. Then it will occupy that volume. So I have given that the weight is equal to mg, we can write, or weight is equal to v rho into g. So this is for the ice. V rho for density of the ice into acceleration due to gravity is equal to v into rho w into acceleration due to gravity. Density of this water is taken as rho w, and volume of the submerged part, S for submerged part. Submerged part is Vs, and G is acceleration due to gravity. So both sides we can cancel G, as they have asked ratio. The volume, the iceberg, if the density of the ice is, so then what is the fraction of the volume that is submerged? Fraction of the volume submerged means total volume is V. No, total volume is taken as Vs by Vs divided by V. We have to take that. So fraction of the volume that is submerged, Vs by V is equal to. So whenever we write that, V is equal to V into density is 0.917. V into 0.917 is equal to Vs into Vs, S for submerged part, into 1. 1 is the density of the water. Therefore, they have asked to calculate what is the fraction. What is the fraction of the submerged part? What is the fraction of the submerged part? Vs divided by V. Vs divided by V is equal to 0.917. Fraction of the submerged part will be equal to 0.917. This option is correct. Then once again I'll repeat. Let us suppose certain portion of the iceberg that is submerged. Let us suppose this is the iceberg. This certain portion is submerged in the water. Iceberg, it is submerged in the water. Certain portion it is submerged in the water. Then submerged part, weight of the submerged part, weight of that iceberg is equal to weight of the submerged part, weight of the liquid, weight of that submerged part, or weight of the liquid displaced by it. Then it will be equal to V for volume, rho for density, density of the ice, into acceleration due to gravity is equal to. It is displaced the water. How much amount of the water is displaced? That equal to Vs. Submerged part, how much it is there? Equal amount, equal volume of the water it will displace, it will remove. Vs into density of the water, it is displacing water, that's why density of the water, into acceleration due to gravity. Both sides will cancel. Then V into rho is given as ice. V into, for ice, what is that density? 0.917 is equal to Vs means what? Submerged part volume into acceleration due to gravity, into density 1. Therefore, submerged part volume is taken as V. Actual volume is taken as a V. Submerged part is Vs, actual volume is taken as V. So Vs by V is equal to, Vs divided by V is equal to 0.917 divided by 1. Therefore, Vs divided by V is equal to 0.917. 0.917. This is the answer. 0.917. Right. This is the first problem. Next problem. An aluminum sphere is dipped in water. Which of the following is true? So water up to 4 degrees centigrade, instead of decreasing its volume, it expands. So up to means up to at 4 degrees centigrade, that density will be more. Density will be more means then opposition will be more. Buoyant force will be more. At the 0 degrees centigrade, less buoyant force will be there. And at 4 degrees centigrade, more buoyant force is there. At 0 degrees centigrade, less buoyant force. And at 4 degrees centigrade, more buoyancy, force of buoyancy will be more at 4 degrees centigrade. then buoyancy will be, force of buoyancy will be less at 0 degree centigrade, and the force of buoyancy is more at 4 degree centigrade. Force of buoyancy, that depends upon the density. At 0 degree centigrade, the density is less, but at density is less means force of buoyancy is also less. At 4 degree centigrade, force means density will be maximum. Then opposition means buoyant force will be maximum at 4 degree centigrade. Next, a cylindrical container containing water has a small hole at a depth of 8 centimeters from the bottom and a depth of 2 centimeters from the top surface of the liquid. The maximum horizontal distance traveled by the water before it hits the ground. See, it is a tank. It is a tank like that. It is taken. It is like this. Let us suppose it is the tank. So in the tank, at a height, h is equal to 8 meters. At a height, capital H is equal to what? H is equal to 8 centimeters. A hole is there. And this is below that surface. At a height, small h from the, at a height below, small h from the top, one hole is there. From the bottom, it is 8 centimeters. From the top, it is at 2 centimeters. Then water will fall from this. Water will fall from this. Water will fall from this. Then it will fall like this. Then we have to calculate what is the velocity at this point. Then we have to calculate what is the horizontal distance. Horizontal distance we have to calculate. D is how much we have to calculate velocity at this point. You know, according to that equation of continuity, if the water falls from a height h, then velocity at this point, velocity v is equal to square root of 2gh. Velocity v is equal to square root of 2gh. V is equal to square root of 2 into g 9.8. V is equal to 2 into g value 9.8 into height is given as height is 2 centimeters above this hole. Then v is equal to 2 2s are 4 into 9.8. That will be v is equal to 2 into square root of 9.8 meters per second. 2 into 10 power 2 into square root of 9.8 meters per second. Then we got horizontal, we got that horizontal velocity. Then what is the time taken to fall down? We will take it. What is the time taken? T is equal to square root of 2h divided by g. It has to fall through a height capital H. That's why capital H is taken. Square root of 2h divided by g. T is equal to square root of 2h divided by g. Then T is equal to square root of 2 into capital H is taken as given as 8 centimeters divided by acceleration due to gravity 9.8. So T is equal to 2 into 8 will be 16. Square root of 16 will be equal to 4. 4 divided by square root of 9.8. This is the time period and this is the velocity. Then horizontal distance covered, D is equal to horizontal velocity into time of flight. So D is equal to horizontal velocity 2 into square root of 9.8 and time period 4 divided by square root of 9.8. Square root of 9.8 to square root of 9.8 gets cancelled. 2 into 4, D is equal to 2 into 4, 8 centimeters. The horizontal distance covered is taken as this is 8 centimeters. Time period, how much we got? Time period is T divided square root of 9.8. Like that, these are given. D is equal to 8 centimeters. D is equal to 8 centimeters. D is equal to 8 centimeters means second option is correct. Right. Next problem. The pressure at the bottom of the liquid tank is not proportional to. So pressure that is arised due to the liquid column is pressure P is equal to rho GH. So it depends upon the density, it depends upon acceleration due to gravity, it depends upon the height, but it is independent on area of the base. It is independent on area of the liquid surface. That's why independent, which is not dependent, they have asked it. It is independent on the liquid surface. Next. Hydraulic lifts works on the principle of Pascal's law. Hydraulic lifts, they work on the principle of the Pascal's law. Hydraulic lifts and hydraulic brakes, they will work on the principle of the Pascal's law. Next. An ideal fluid flows through a pipe of circular cross-sectional area of diameter 5 centimeters and 10 centimeters shown. The ratio of the velocities of the fluid at A and B. The diagram, I didn't keep it. Actual diagram is like this. They have given actual diagram like this. So different area of cross sections are there. Area of cross section A1 is 5 centimeters. Area of cross section is 5 centimeters. At here area of cross section A2 is equal to 10 centimeters. They have given. Then velocity at this point is taken. Then and shown the ratio of velocities. So this is area of cross sections are given with the diameters. Sorry, they are given diameters. A1, A2 are the area of cross sections. A1, A2 are area of cross sections, and diameter nothing but radius. Radius is taken as R1 and its radius is taken as R2. Now radius is directly proportional to diameter. We may take radius is proportional to diameter. Then velocity at this point is taken as a V1. Velocity at this point is taken as V2. V1, V2 are the velocities at cross-sectional area A1 and A2. Then according to equation of continuity, V into A is taken as a constant. Then V into A is equal to pi r square. V into pi r square is taken as constant. So V into R square is taken as a constant. From this we will write V is inversely proportional to R square. V is inversely proportional to R square. Then we'll write V1 divided by V2 is equal to R2 divided by R1 whole square. What is this? V1 by V2 is equal to R2 by R1 whole square. V1 divided by V2 is equal to R2 divided by R1 whole square. I have rewritten again. V1 by V2 is equal to R2 is 10. R1 is equal to 5 whole square. For 10 that cancel in 5 that cancel in 2 times. So V1 divided by V2 is equal to 2 2s are 4. 4 is to 1. 4 is to 1. First option is correct. Next problem. If flow of fluid is streamlined, if the Reynolds number is, if the Reynolds number is a pure number, it will give that nature of the fluid flow. If the Reynolds number is less than 1000, it is called as the streamlined flow. If the Reynolds number is greater than 1000 and less than 2000, this is called as the uneven flow. If the Reynolds number is greater than 2000, nothing but Reynolds number, if it is 3000, it is called as a turbulent flow. Reynolds number is a pure number that will give the nature of the flow of the fluid. So a flow of fluid is streamlined if the Reynolds number is less than 1000. If the Reynolds number is less than 1000, then fluid flow is streamline flow. Streamline flow means what? Steady flow. Like this, without any deviation, the liquid flow will be straight line. This is called streamline flow. Uneven flow means what? How to take that uneven flow? This is called as the uneven flow. And what is called turbulent flow? This is called as the turbulent flow. Turbulent means making turns. So if the liquid Reynolds number is less than 1000, it is the streamline flow. Next, the two solids P and solids P, two solids P and Q floats in water. It is observed that P floats with half of its volume immersed, and Q floats 2/3 of its volume is immersed. First one is first one is observed that water is flowing with wet. First one, half of the volume is immersed. First one is half of that one is immersed. Second one is only 2/3 of its volume is immersed. Then the ratio of the density of P and Q. Once again, I'll say that two liquids, two solids P and Q floats in water. Q is missed here. It is observed that P floats with half of its volume immersed and Q floats with 2/3 of its volume is immersed. Then we'll take this weight of the P is equal to weight of the water displaced. Weight of the P is equal to weight of the water displaced. There we will write weight of the P is equal to Vp into rho Pg is equal to how much part it is? Only half of the part. So then now Vp divided by 2. Half of the volume is only that floats. So V by 2 into density of the water into acceleration due to gravity. Both sides G gets cancelled. Then Vp also gets cancelled. Density of the water is taken as a 1. Therefore, density of the P is equal to 1/2. Density of the P is equal to 1/2. 1/2 that we will get. Density of the P is equal to 1/2. Similarly, we will take for that second also. So weight of the Q is equal to weight of the water displaced by Q. Then volume of the Q into density of the Q into acceleration due to gravity is equal to how much part is it is submerged? It is 2/3 of its volume is it is submerged. Then 2/3 VQ into density of water into acceleration due to gravity. Both sides we will get cancelled. Will get cancelled G. Then VQ also will get cancelled. What it will be there? Density of Q is equal to 2/3. It is the equation number 2. So the ratio of densities of P and Q they have asked. Ratio of the densities of P and Q. Equation 1 by equation number 2 if you take. Density of the P divided by density of the Q is equal to, this is 1/2 whole divided by 3/2. It will come to numerator. So density of the P divided by density of Q is equal to 2 divided by 2 3s are 6. 2 divided by 2 3s are 6. 1:2. That is 2/3. Sorry, I will written reverse. This is a 2/3. This is taken as a 2/3. This 3 comes to numerator. That will be, therefore, density of the P divided by density of Q is equal to 3 divided by 4. 3 divided by 4 it is. Right? This is the expression. Then I'm going to stop the class here. We'll see that next concept in the next class. Thank you.
Thank you, sir.
Sorry, I didn't share.